Okay, today we're going to cover the first part of thermochemistry, which is going to be the nature of energy. And we have to define a few things first. The first is energy, and we're going to define energy as the capacity to do work or to produce heat. And then also the law of conservation of energy, which we are going to define as the fact that energy may be converted, but not created or destroyed. Very similar to the law of conservation of mass. And the key here is converted, and we're going to see transferred as well. Those are going to be the big major thoughts here. Now for types of energy, there's two major types of energy, so we can get this out of the way. The first being potential energy, which is due to the position or composition. And for example, if you look down here for the water that is at the top of the waterfall, this water has potential energy because of its position at the height of where it is. And from a chemistry perspective, attractive or repulsive forces are usually potential energy that can eventually act on something. On the other hand, we also have kinetic energy. Kinetics means motion, so this is the energy due to the motion of an object. The equation for kinetic energy is 1/2 mv squared, meaning the mass and the velocity, so how fast it's moving in a certain direction, as well as the amount of material there. And as you can see down here with this picture, as the water begins to fall, it starts to convert potential energy to kinetic energy. We get more potential energy converted to kinetic energy here. And last but not least, all of that potential energy has been converted to kinetic energy on this last slide. Excuse me. Now also we have another slide here where it talks about two different situations where A is an initial set of conditions and B is a final set. Now if we look at A, this is just the idea that the potential energy of position A is greater than the potential energy of position B, and again that's due to positional differences between those. Now in B, or the final setup here, we have the fact that ball A has rolled down the hill and it has lost potential energy both to friction and potential energy in ball B, because now you have B with the positional stored energy, and that energy was transferred as A came down, transferred its energy during this collision and allowed B to move up and now have the potential energy. As a side note, thermochemistry and thermodynamics is where a lot of chemistry and physics overlaps. We start talking about things like friction and energy, and these are things that are also classical physics subjects as well, so you kind of get both in these situations. Okay, now we're going to talk a lot about heat, and we have to differentiate between heat and temperature. They're two terms that are very easily confused. Temperature, our definition of temperature, is not going to be the scales that we measure it with, whether it be Kelvin, degrees Celsius, or degrees Fahrenheit, but temperature is a measure of the average kinetic energy of the particles. And we talked a lot about this in Chem 1, in that temperature and kinetic energy are directly related, and that if you increase the kinetic energy of something, you also increase its temperature, and vice versa. If you decrease the kinetic energy, it's going to decrease its temperature. So they are directly related. Now there are two ways to transfer energy in a system, and they're very different, so we need to make sure that we define them both and keep them straight. The first is with heat. Heat is abbreviated with the letter Q, and it is the transfer of energy between two objects because of a temperature difference. Okay, now one thing that's really important in thermo is the fact that we always talk about the flow of heat and things either losing or gaining heat. We don't talk about things getting colder. We talk about either losing or gaining heat in this transfer of energy. In reality, whenever you have a temperature difference, there's always some flow of heat, okay, whether it be bringing something to room temperature or forcing a temperature to change. And the second one is work. Okay, now work is force acting over a distance. And here's our equation for work. And again, this sounds very physics-minded, which it is, but if you think back to the last slide, work was required to raise B from its initial position to its final position. So there's two different ways to transfer energy. You can have heat energy or you can have work. And so we just need to make sure that we define those and we keep those straight. Now, when we talk about the transfer of energy, we have to keep in mind the perspective. And we're going to have two very simple definitions that we use in chemistry. when we talk about the system, that's the part of the universe that you're focused on. So very frequently in chemistry, when we're talking about thermodynamics, I'll draw maybe a small circle or a box and talk about if energy is flowing out of that system or if it's flowing into that system, okay? In the surroundings, we're going to call everything else in the universe. Now, I realize that's a big area, but we're either talking about the system, our chemical reaction, or everything outside, okay? So we're either going to have our system or the surroundings, which I think is pretty straightforward. Now, typically when we talk about perspective, like I said with chemistry, the system is what's in the room and the surroundings are really, the system is what's in the container that we're studying, the surroundings is the room, maybe the container itself, and that's going to be a little bit different. When we're talking about, a beaker, there's my lovely little beakers again, when we talk about the system is really just the chemicals. Let's say we've got sodium chloride solution. Okay, the system would just be the sodium chloride solution itself. The surroundings would be everything outside that solution, so the container, the room, etc., etc. And I know this perspective thing is going to seem really easy in the beginning, but it's something that people just really get stuck on. Now, with transfer of energy, there's two terms that we should hopefully remember from last year. The first one is exothermic, where energy is produced in the reaction, so energy is then flowing out of the system. Right? And then secondly, we have endothermic, where energy is consumed by the reaction and it's flowing into the system. We talked a lot about this last year. In fact, we overgeneralized, talking about where exothermic is usually warm, endothermic is usually cold. We stay away from those generalizations in AP because sometimes it ends up getting us in trouble, as we found when we oversimplify things. This is just another slide to identify this, where again, in exothermic, it's this whole idea that heat is leaving the system, okay? It's going from the system to the surroundings. And then endothermic, on the flip side, is going to be where heat is transferred from the surroundings to the system, okay? And I know it seems very obvious, and that's a good thing, but I'm going to draw a lot of these little circles to show the flow of heat, because sometimes in all the specifics we have to focus on, we get lost in the details. Okay, now with the transfer of energy, this is a reaction where you have the combustion of methane. You've got CH4 and oxygen being lit on fire and combusting, and releasing all of this energy. Our y-axis is potential energy here. Okay, so that combustion reaction is releasing all of the energy that was stored in these chemical bonds in the reactants, and we get two new products. We get water and we get carbon dioxide. And energy is going to be released into the surroundings as heat. So this is a graphical representation of an exothermic reaction. Okay, and also you'll notice that the products, anytime the products have less energy than the reactants, it's exothermic. That stored energy was released, and the products have lower energy, which is also something that makes molecules and atoms happy. They want to have low energy. Okay, now on the flip side, we have situations where sometimes it requires an input of energy. So if you have nitrogen and you have oxygen, and you add enough heat from the environment, you can force that chemical reaction to take place and get into a situation where the products have a higher potential energy. In this situation, the heat has to be absorbed from the surroundings. That's what allows the energy to increase, and so this is going to be an example of an endothermic reaction. Okay, again, you've just got a graphical representation of that. Now with thermodynamics, they really kind of overlap. Thermochemistry is the study of energy in chemistry. Thermodynamics is really just more focused on the energy and its transfers anywhere. So it's kind of a bigger, broader, picture. If you think about a Venn diagram, or not a Venn diagram, but just a circle diagram, where thermodynamics maybe is the bigger case, or the bigger subject, and then thermochem is included in that, so it's a part of thermodynamics. Okay. Now, the first law of thermodynamics is that energy of the universe is constant. You may go, okay, well, that's great. And that just kind of goes along with the mindset that energy is always transferred, that it's got to go somewhere. It's not just spontaneously produced or spontaneously disintegrated. Ooh, that was fancy. Okay, now again with our first law, there's an equation. We always got to have the math. Okay, delta E is equal to Q plus W, where delta E is a change in the system's internal energy. And all this is talking about is that perspective about that the energy, we're going to focus on the system's perspective. Physics can be a little bit different. Engineers treat it a little differently in the surroundings perspective, so we just want to make sure that we keep that straight. Now the next thing, it says kinetic and potential energies of all the particles in the system. So again, since we're talking about chemistry, we're thinking about the kinetic energy on a particular matter, or a particular level, and what that means for the atoms and the compounds that are, for the molecules that are floating around. Q is heat, W is work, and the internal energy of a system can be changed by a flow of work, heat, or both. Okay, and this is essentially a mathematical way to study that concept. Okay, and it goes back to the idea that since there were two ways to transfer energy, which include heat and work, there's two ways that a system can have its energy be changed, and that's also with work or heat or both. And of course there's going to be some math related to that. Now again, we're talking about internal energy. I know this is kind of a repeat, but just to really drive this home, that it's the sum of the potential and the kinetic energy in the system. It can be changed by work, heat, or both. And then we've got also our energy being potential energy plus kinetic, which again we have our delta E is Q plus W. And just as a reminder, we have energy flowing out of the system to a surroundings. It's usually going to have a negative sign. That's going to be exothermic. And when energy is flowing into the system from the surroundings, it's going to be endothermic. Really driving home the surroundings versus systems point. Now these signs are something that's going to be important. We're going to focus on these in some practice problems, but the signs will always reflect the system's point of view. We're going to see that it's not always absolute. We're going to talk about some situations where you have plus and you have minus, or opposite signs between Q and W. We'll talk about if it is what we refer to as spontaneous or not. But typically if it's exothermic, you've got a negative change in energy. The heat is flowing out of the system and the work is flowing out of the system. Endothermic is going to be just the opposite, where the energy is, the positive is, the change is positive, heat is flowing into the system, and work is leaving this, or work is flowing into the system as well. And again, this is just reminding us this whole surroundings system perspective. If energy is leaving, it's going to be exo, and if energy is coming in and it's positive, then it is going to be endo. Okay? Now here's one math problem, and again, as always, if you need more detail, there is more detail in your textbook, as well as the additional Khan Academy videos that I've listed. So there's other resources out there. But for this one, it wants you to find the delta E for endothermic process, where 15 kilojoules of heat flows and 1.4 kilojoules of work is being done on the system. Now since it's endothermic, Q is going to be positive and W is going to be positive for right now, okay? And really all we have to do is add them together. We've got our equation, so we always want to show our equation. We add our units with significant figures. It's the fewest number of decimal places, so if I show you the old school way, 15.6 plus 1.4, we're going to end up keeping one decimal place, so it's going to be 17.0 kilojoules. And just as a warning, you got to keep an eye out on kilojoules versus joules in this unit. Sometimes the book and myself does a bad job of flipping back and forth, and sometimes that's where we get the confusion on which units things need to be in. So, and if it doesn't specify, typically I will accept either kilojoules or joules, whatever your final answer is. So, okay, I hope that